the main things.
Wait, what did you do?
Did you do the cross product? This is the surface involved. Yeah, this is row. 2. So yeah, so substituting 2 before I do the cross product here. And then you get that one thing.
Yep.
What's even? Salt versus.
Yeah, that's the whole use.
What do you, what
Hold on.
do you do?
X and
You
Y.
do R, U, and R, U. So
You
you
do,
solve
you
for
do,
T.
you do X, Y, yeah. So it'd be
X,
parameterization
Y,
X,
and then
Y,
4.
square root X squared plus Y squared.
Is that number 2?
Yeah. Wait, which one's the field, the force, and vector field? What's that?
No, this is, it's different. This is like surfacing when it asks from above this cone. This is a sphere, what is the like? So this area.
All right, guys, ask away.
Were we done with the question we just went over?
What were we doing? I don't even remember.
It was
10,
number 10.
web work in 10.
Got it.
Just 10.
Oh, the picture one?
Oh, do I have no internet here? That sucks.
You.
Try again, maybe? No? Okay. Oh, there we go. Whitman Wireless, try that. Come on, stupid thing. Okay, that's better. And web work. And I bet I'm not going to be able to type on this thing. Let me switch over.
Put the team on the back.
All right. So, see this this thing right here? That makes the equator instead of being yeah, I know. That makes the equator instead of being in the XY plane, it puts it in the YZ plane, and possibly that's enough for whoever answered the question. I don't know.
I'm going to try.
Okay.
Are we going to ask questions not on the web work?
Yeah, you can ask any question that you want, Chelsea.
Oh, my turn?
Sure.
Okay, could you do 16.7, number 1? It's the mass and center of mass question.
Okay, I think somebody was already asking about that, but let's do a quick review here. Okay. Which one in particular?
Number 1.
Number 1.
Did you already do it?
So, well, I can talk about it. So, to find the center of mass of this object, essentially what you have to do is build this integral.
Mhm.
So the mass is the integral over the surface S sigma ds. Okay, and this is not d vector s, this is just ds in the sense of ds is equal to ru cross rv times du dv. the surface, let me go back to the book here. You have to parameterize the upper hemisphere using spherical coordinates. So if we do spherical coordinates here, we get r of u and v is equal to sine v cosine u, sine v sine u, and cosine v. Let me just double check that there was no radius on that. The radius is 1, good. Okay, so now we have to be careful with the parameterization. So v is playing the role of phi in this problem, and u is playing the role of theta. So we have 0 less than or equal to v less than or equal to pi over 2 because it's just the upper hemisphere, and 0 less than or equal to u less than or equal to 2 pi to sweep out the entire, all the way around. So then you would do ru.
I can do this.
Yeah, okay. So then you do ru cross rv, yada, yada, yada. Okay.
Just messed up.
Okay. Next. Same one. So now you're asked to evaluate f dot n ds, and you don't have the divergence theorem at your disposal here. This is just really just doing the surface integral. Okay, so was it 7 you said? Let me just put a note here. So D is the surface given by, you take a paraboloid, which is z equals x squared plus y squared, and you flip it over, and then you add 1 to it. So that's 1 minus x squared minus y squared. So it's a parabola opening down, and the vertex of that paraboloid has been shifted up 1 unit along the z-axis. And then we are restricting our attention to x squared plus y squared less than or equal to 1 in the xy plane. So that's the piece of surface that we're interested in. You can parameterize this either using spherical coordinate, either using polar coordinates or Cartesian coordinates. Let me show you both. So let's look at that. What is this? 16.7 point? Gosh, 6, 7, 7. So we have z equals 1 minus x squared minus y squared. For Cartesian, you would do something like r equals x comma y comma 1 minus x squared minus y squared, and then go through that whole, rx, r. Or you could do this in polar, and then you would do r, and this is not the same r, but r cosine theta, r sine theta, and then 1 minus r squared. And for this guy, you would be restricting yourself to the domain x squared plus y squared less than or equal to 1. And for this guy, you would be doing 0 less than or equal to r less than or equal to 1, and theta between 0 and 2 pi. And then here you would do, I don't know, I should have chosen different variables, but you could say s sub r and s sub theta, and then s sub r cross s sub theta, etc., etc. In either case, when you get to this integral here, you can replace nds with ru cross rv du dv. Right? It's very rare in the exercises that we've been doing that you actually compute capital N, right? Capital N being the normalized, being the unit length normal vector. But before you go on, you have to replace x and y with your parameterization. If you're using Cartesian coordinates, these guys stay exactly the same. If you're using polar coordinates, then this changes to r cosine theta, r sine theta.
So would you recommend, at least I think sometimes it works
better to keep it in Cartesian until you've done the dot product and then switch to polar? Is that a good strategy?
It's a wash. It
Yeah.
really is. Whatever you feel comfortable with. So just remember that if you keep it Cartesian and then you change to polar at the end, you're going to use r d theta.
Right.
And if you do polar from the start, then you don't do
Right.
r d theta. It's just dr d theta. Okay. Next question.
I was studying divergence in curl, and there was a notation that I didn't recognize. It was the double integral of the region D of nabla across F dot K dA. Does that just mean, and that's equal to Qx minus Py, so does that just mean you're dotting it with like the K vector, which would
Yes,
make it
and
okay.
you were probably in the divergence and curl section. So if you go back to the divergence and curl section here, they introduced the divergence and the curl notation, and then they used that notation to rewrite Green's theorem.
Right.
And in the recast version of Green's theorem, maybe I'm wrong about that. I thought that was in this section.
I think it is. I think it's just up.
Okay.
Yeah.
Ah, yes. So that's this guy. And then Stokes' theorem is really a generalization of this thing where you replace K with N, a normal vector.
Right. Okay.
Okay. Next.
I have a question on 16.6, Messenger 11. I'm
Okay.
just having a hard time with when I get to my integral, solving for it. I get,
So what are we doing? Surface area in this problem? Yeah. Okay. So go ahead.
so I mean, you parameterize you find r of x and rxy.
Mm-hmm.
You do rx and then ry, and you take the cross product and the magnitude of the cross product.
Yes, that's right.
Okay.
It's a lot of work.
Yeah, then in my integral, I end up with the square root of a squared over a squared minus r squared.
Sure, I'll believe you.
Yeah, how do you solve it?
I suspect that what you want to do is jump ship and go. I want to say. I'm just trying to see ahead here. I'm guessing that you want to go polar on this.
Yeah.
Okay, so maybe I'm not seeing. Okay. I'll buy that. Okay. Ah, mm-hmm.
You got my error?
No, still just, okay, I think you did this largely correctly. So when you did your use substitution here, you should do one of two things. Either switch back to the R variable and then use these guys, or change.
But how do I find the integral of the u to the negative 1 1/2? Is that possible?
So that's u to the minus 1/2, right?
Oh,
And-
oh.
Next question. Sorry, that wasn't enlightening to everybody, but it was good for Chelsea.
Sorry, guys.
Sky.
Well, we already talked about this one, but it was the, let's see, it was the one for 16.7.1. It was that center of mass one.
Yes.
and then it has density x squared plus y squared, so because we parameterized it in spherical, we plug in the spherical
X and the
parameterization,
spherical
so
y.
it'll be this weird.
It won't be, it's not terrible.
Okay, but that's just how we changed, so but we put the parameterization into x squared.
Yeah,
plus y
so
squared. That-
this isn't quite that parameterization. Let me double check here. So this is, oh, I guess it is that parameterization.
Yeah.
So you take this guy and this guy and this guy and drop it in, and x squared gives you sine squared cosine squared, and this gives you sine squared sine squared. And what you're going to get out of that is a Pythagorean identity, and you're just going to end up with sine squared v.
Yeah.
And so it won't be as bad as you might suspect. All right. Katie.
So there's two formulas for surface area in this chapter. There's one that's just the magnitude of RU.
Yes.
And there's one that's the function times the magnitude.
Yes.
What's the difference when you use which?
The only real difference in these two sections is in the second section we allow for the possibility. So in the first section, essentially all you're doing are integrals like this. So let me go back here. You're always doing integrals like this, which we recognize by our notation. And this is section 16.7. 16.8 is really nothing more than dropping a function in there. So
What does that mean geometrically?
the best I can do for you is density. So you're taking a little piece of density and multiplying by, you're taking a little piece of surface area, ds, and multiplying by the density of that thing. That's the best I can do for you in that regard. Although later we talk about flux and the idea of taking a little piece of surface area and measuring the component of some force field that's crossing that little piece of surface area. So there's two kind of different geometric interpretations that we encounter, the flux integral and then the mass/density kinds of problems.
But they're the same computation.
But they're the same computation. Essentially, you're either sticking a sigma in here, which is a density, or you're sticking f dot n ds. Now, what kind of function, scalar or vector, is sigma? It's a scalar. It's not a vector-valued function. It's a scalar. What kind of function is f dot n? Scalar or vector? It's also a scalar. So there is effectively no difference between these two integrals. They just mean different things. F dot n gives a scalar, just like sigma is a scalar. Okay. Next. Logan. Yes. See you, Nina.
16.6, number 5. I mean, it seems simple, but I just don't know where to start. I know I probably wasn't parameterize it.
Find the area that lies below z equals 1. So this is a paraboloid opening up, and then it's cut off by, okay. So the surface that you're interested in sits above the circle of radius 1 in the xy plane. Yes? So that's going to be, that's going to define the domain of integration for you, the circle of radius 1, when you get to that point. Other than that, x squared plus y squared, let's go look at that. I've already forgotten. 16.65. So now you just go through that whole Rx, Ry, Rx cross Ry, and then the magnitude Rx cross Ry. And when you finally get down to it and you integrate this thing, right, now you've got this domain of integration x squared plus y squared less than or equal to 1. At this point, I would go polar. Okay.
I wasn't just sure where everything came from.
Yep. And again, you could also choose, so here you would go polar, or you could choose to parameterize this from the get-go, r cosine theta, r sine theta, and r squared. And then when you get to the end, you're going to have essentially the same integral, you just don't convert to polar because it's already kind of there. And then the only other thing to be careful of when you do this is that you choose, oh no, when you're doing magnitude it doesn't matter. I was going to say choose the upward pointing
So
normal.
if I started with the polar coordinates, like with doing r cosine theta,
Yep.
cosine theta, r squared, then when I go to do my integral, I don't have to multiply by r.
Exactly. Yes.
Okay.
Yep. If you
But
start out in polar,
when I
then when you get to the end, no. But if you start out in Cartesian and change variables,
Okay.
whenever there's a change of variables, you have to introduce those extra Jacobians.
No one wants to multiply all those trig functions. So in that case, you took the magnitude of it.
Yes.
Why in other cases do you just do rx cross ry?
So there are
Is that
two
what you're
different.
doing?
There are two different. Right. Let's go back to my notation page here. Here. So sometimes you're dealing with D capital S, but it's not bold-faced. Right? D capital S is always that. And then sometimes you're dealing with this guy. Now, the reason that sometimes you work with this and sometimes you work with this is the fact that this is a unit normal vector. Right? This is the unit normal vector to the surface. So that's RU cross RV divided by the magnitude of RU cross RV. Right? So RU cross RV divided by the magnitude of RU cross RV. And then ds is the magnitude of RU cross RV du dv. When those two guys multiply together, there's a cancellation that occurs, and it leaves behind just the cross product. So the difference here is D capital S and D boldface S.
And we'll see either one.
You're going to encounter both of these, yes. Okay, next question. Sky.
So I'm just trying to figure out, and it might be way simpler than I'm making it, but like when you do a surface integral, that sometimes you have to take multiple integrals, like top and side and bottom.
Yeah.
Like I'm just trying. How do you know which ones to do and when to do it? Because it seems like sometimes you don't need to, and sometimes you do need to.
9 times out of 10, you avoid doing multiple surface integrals by applying the divergence theorem.
Okay.
And I guess that's the best advice I can give you. So there may be situations where you have to literally glue together a bunch of surface, a sort of Franken surface kind of thing, where. But even in Stokes' theorem, right? I mean, we saw that one where we had this cylindrical band, and then there was like a hemispherical cap, and we avoided doing those two surface integrals by instead using Stokes' theorem around the boundary of the opening. So Stokes' theorem can help you avoid that, and divergence theorem, in fact, can help you avoid that. I would definitely, if I encountered a surface integral and I felt like I was heading down the road of doing multiple surface integrals to just, and then I was going to add them together, I would definitely look really hard at either Stokes' theorem if the surface is an open surface, and divergence theorem if the surface is a closed surface.
But then we can do that, but then also, like, I guess I'm also asking, like, for different surfaces, just which, even though you don't want to do multiple integrals, if you were going to,
Then you would have to find a parameterization for the first surface and go through all that crap,
So like for a cylinder, you'd have to do the top and then the bottom
the sides and the bottom,
sides.
all separately,
And
all
as long as
separate
you find a
intervals.
parameterization that works for all three of those, that's how you do each interval.
Yes.
Okay.
And I will say that often, for example, that cylinder problem I think we did in the review sheet on Monday, that top and bottom surface integral, that those tend to be pretty easy because
Yeah.
the normal vector is constant everywhere. And anyway, and then like the bottom part of the cylinder, z was equal to 0 as well, which also helps. Anyway.
Can you go over number 11 on the web work?
Yes.
I think in just setting it up, I was getting something wrong.
All right. Now here's a nice problem, Sky, that's related to what we were just talking about. If I were going to do the surface integral, and I'm not sure that's what's being asked for here. It looks like, yeah, we're doing a surface integral. The top and the bottom flux integrals are both going to be 0. Why is that?
Because it seems like all the vectors are parallel to the surface.
Perpendicular, parallel to the surface, perpendicular to the normal, right?
Yeah.
So if you took a normal, this thing, it would be pointing straight up. When you dot that thing with the field, you're going to get 0 everywhere. So if you were going to do the surface integral across this whole volume, you'd only have to do the surface integral around the cylindrical side. And then you can just ignore the top and the bottom because the normal vector is perpendicular to the force field. Okay, but that may not be the way we want to go here anyway. So the big hint here is divergence theorem. So this suggests. Oh, in fact, it
Yeah,
says.
it asks you to do it through the divergence
Yeah,
theorem and
so
then
go ahead.
find it the other way. And I was getting the answer, but for some reason it was twice what the actual answer was. So
Okay.
I was wondering if you could.
Did you? So essentially, we want to do f dot dA, and we know by the divergence theorem that the integral f dot dA, that's the same as, just notation check here, f dot n ds, which is the same as the triple integral of the divergence of f dv. So now let's go back and see what the divergence of my f is. Your f may be slightly different. The divergence of my f looks like it's just 4.
Yeah.
Yeah. Okay, so that's the integral of 4. So it's 4 times the volume integral, and so now I'm just left with computing the volume of the cylinder. And the volume of the cylinder, maybe that's where you're getting tripped up. Let's see, this is a cylinder of vertical height 4, and its base is a circle of radius 4. So the area of the base is 16 pi in my case, times 4. Is that 64? So 64 pi, that's the volume, and then I need to multiply by 4, which is that thing sitting out front. So it would be like 4 times 64 pi, which I'm guessing is like 256, I think. So let me just check my answer. Okay, so 256 pi. So does that help you explain where you're off by 2?
No.
You mind if I pull up yours? So yours was 2. The height was 6. The radius 2. So let's see, we've got 4 pi times 6.
So is this correct? So it's just
Oh,
2.
so you're going to do the integral.
Well, it's just like, just in terms of
Okay,
setting
yeah,
it
that's
up,
fine.
that is
Sure.
correct, though.
So let me just stare at it for a second. 0 to 2, 0 to 2 pi, and 0 to 6. Yeah, I'll buy that.
Okay.
And then a 2
So then
from the divergence. Yeah.
Okay.
Can I see? Let me keep looking. Oh, right here. That's r squared.
Okay.
This one,
Multiply by r.
polar, then you'd say
You'd got most credit for
it's
that.
from z is from 0 to 6, r is
Volume
from
of
0
a-
to 2,
Volume of
and
cylinder
theta is
is
from
pi
0
r
to
squared
2
h.
Yes, a right circular cylinder,
Okay.
r squared h. Yeah. Right, you could have not a right circular cylinder, but like a circular base, and then it's slanted over or something. Then things get crazy. But yes, a right circular cylinder. Yes. Next question. And I'll stop acting as Chloe. There.
Well, I have a question from the Stokes section of the book.
Of the book, okay.
It would be number 16.8, number 3.
So now we have the portion of the plane inside x squared plus y squared equals 1, oriented up, and f is that thing. Compute the line integral.
So my question
Mm-hmm.
is, I remember in one section of the book you talked about how z needs to be positive. And
Yes.
And is that when it says oriented up?
Yes.
Okay. So you multiply the whole thing, the whole cross, the whole curl by -1.
Curl.
Or
Not necessarily.
if I was doing,
So, but when you, let's pretend that doing the surface integral is the right thing here, right? Remember with Stokes' theorem, you kind of have a choice. You can do the line integral or you can do the surface integral. Let's pretend that doing the surface integral is the right thing. So then this line integral becomes, I forget, 8, 3. So we have this line integral df dot dr is the surface integral over d curl of f dot n ds. All right. So if you were going to parameterize that guy, let's say you're going to do the surface integral, then you have to build a parameterization.
I have the whole problem written down.
That's okay. It's probably good review. 2x plus 5y.
No, and then I had the question.
Oh, got it. It's so rx 1, 0, 2, ry 0, 1, 5, and then rx cross ry is going to be -2, -5, and 1. So that is up.
So that needs to be up.
Yes.
It doesn't matter if the curl of that is.
No, the curl is the curl. You don't get to play with that.
Okay.
Yep.
And is this the only section, whenever it says oriented up, z needs to be positive?
The third coordinate, yes.
So can we finish setting it up all the way to the double integral? Can we
Sure.
do the curl and then?
So the curl of f and then I don't remember what f is. Chelsea, do you remember?
Yeah, f is y, comma, z, comma, -x.
Like that? Okay. So let's do the curl of this thing. That's 0 and -1. That's going to be -1, 1. and that's going to be -1. So I think that's the curl.
Yeah.
And you don't fiddle around with that. You're stuck with that. So now you want to dot that with Rx cross Ry. And the dot product there is 2 plus -5 plus -1, it appears. 2 plus -5 plus -1. That appears to be -4. All right. And now you're ready to do the integration. So we want to integrate -4. So this whole bit in here turned into a -4. So all that work got us that -4.
And then we just do apply the limits. I don't know.
Yeah, and the limits were inside a circle of radius 1. Is that right, Chelsea?
Yep.
Okay, so now you've got -4, but you've got dy dx.
Yeah.
So now you should go polar to make your life easier. In fact, you don't even have to go polar. Just pull that -4 out. And then multiply by pi r squared, which in this case is pi. So hopefully this is -4 pi. Yes. Okay. Go ahead, Logan.
This goes all the way back to like the fundamental theorem of line integrals.
Okay, good.
So we would use that just whenever we're asked to find a low f, and then we find the f and then just plug in the points we're given.
Yeah, and if you ever encounter a line integral, you know, before you go herring off and trying to parameterize the curve and all that kind of stuff, check and see that if it's conservative. If it's conservative, then use this fundamental theorem of line integrals.
And the test for conservativeness is if nabla cross f is 0, or what is it? It's huh? Oh, Q.
Well, if it's a two-dimensional vector,
It's Q is what Q, but it was 3.
if it's three-dimensional, yes, you can use the curl. If the curl is 0,
Okay.
then, or you can memorize the 3 conditions. The 3 conditions actually are perfectly equivalent to the curl being 0.
It's just that that k. For two dimensions, it's just k.
Right.
The curl has to equal 0. Okay.
Hannah, did you have a question? You came in.
Well, I just keep getting confused where sometimes it has like double integral of like curl times the normal, and sometimes it just says f times the normal, and it's like hard to tell. The
Can you give me an example?
Um,
Or 2 examples?
well, I guess when they're just describing flux for different things, like when you emailed us the terms, it just used double integral n times or f dot n. But then, like in the book, when it's describing Stokes' theorem
Mm-hmm.
and stuff, it uses like curl times n.
Yeah, so this is a vector field right here.
Yeah.
Okay. The curl is also a vector field, right?
Yeah,
The
it
curl of
looks
f. So it's just a matter of what vector field do you want to put in there? Do you want to put f in there, or do you want to put the curl of f in there?
What does the result mean? Significant, like.
It's very difficult for me to describe what having the curl of f in here means. I can try. I'm not sure how valuable it's going to be.
How you would know when to use it.
Well, when does that curl thing come up? It comes up when you're doing Stokes' theorem.
So you just do it when you're doing Stokes then?
Yeah, I mean, I don't want to sort of make it into a recipe or something,
Yeah.
but Stokes' theorem is a statement that relates the tangential component of the force around the boundary to the flux of the curl across the surface. And that's just it. Stokes is what it is.
Okay. My other question is like finding normals. It says it's a unit normal, but that doesn't mean that its magnitude is 1, right? Because it seems like we keep using ones that aren't.
Right. So let me review.
Because like in the last problem, right?
Let me review that a bit. So we know that D capital S is this thing.
Yeah.
And we know that d bold s is this thing. Okay? This guy here is this divided by this. Right? That's a unit normal vector to the surface. Right? RU cross RV over the magnitude of RU cross RV. So, I take this guy, this is RU cross RV over the magnitude of RU cross RV, and this guy has a magnitude of RU cross RV sitting in it, and it cancels. And what's left behind is this thing. So the reason that we often do not use n is because we immediately do that cancellation.
Okay, so, yeah, so n is a unit vector, but you don't usually calculate it?
Exactly, we rarely I can't think of a single instance in chapter 16 where we actually calculated n.
That was really confusing, because it would have all these vectors that were not
Right.
unit.
Yes.
Vectors. Okay.
And it's because of that cancellation.
Can you sort of set up or, I don't know, explain how you'd start doing number 7 on the upward?
Okay, you know how to do the gradient of f, presumably. Partial of f with respect to x in the first coordinate, partial of f with respect to y in the second coordinate, partial of f with respect to z in the third coordinate. Do that, and then whatever you get, take the divergence of that thing. Turns out, having been a mathematician for a while, I know that this turns into the second partial of f with respect to x plus the second partial of f with respect to y plus the second partial of f with respect to z.
That's what I was thinking, because it seems like you do the same thing twice.
Yeah.
Okay.
That's a slick way of writing something called the Laplace operator, which you run into in quantum mechanics when you're using the Schrodinger operator. So, for example, the second partial of f with respect to x just gives me what, 2a? Second partial of f with respect to y gives me 6y, I think. Yeah. And the second partial with respect to z gives me 0.
Could you write out what?
And I don't even know if they want the third coordinate in here. They probably don't. Sorry, what was the question?
Could you, like, just write out what the divergence of the
Sure.
just the notation?
Just do the whole thing here. So the gradient of f in our notation is this. And for a three-dimensional vector, it's the partial of f with respect to x, with respect to y, with respect to z. That's just the definition, and it only works on a scalar f. It doesn't work on a vector f. Now, if you want to take the divergence of that thing, is that what we're supposed to do?
Yeah.
Yeah. In our notation, that would be this dotted with this. Well, if I dot that, then what I end up with is fxx plus fyy plus fzz. And this is actually has its own notation. That's the Laplacian of f. It's an upside down nabla. Yes.
No more notation.
So the one-
Had enough. Don't make it.
So the one that says find a, so that equals 0 for all x and y.
Yes.
How would you?
So when you do this, ax, so let me just do this, axy plus ax squared y plus y cubed. Or actually, I'll just show the answers, that way I won't have to compute it. Okay, so the answer is 2ay plus 6y, right? And find a so that this thing is equal to 0 for all x and y.
Yeah, just say it.
Set it equal to 0 and
Okay.
solve for a.
Okay.
Yep. Okay. And in that case, f is known as a harmonic function because its Laplacian is 0. More than you want to know right now.
I'm wondering if you can do some of the picture. I don't really care which one.
Well, you're going to have to at least direct me to one, because otherwise I'm just going to...
Which one?
Number 1 was pictures. Number 4 had pictures.
On this review web work
The 1,
thing?
4, and 6, but I didn't know if there are any people found how we do
Like number 1 here?
it. Yep.
Okay. So... what are we supposed to do? Match each vector field with its graph. Yeah, this is a good one. I like this one. Okay, so the first guy has only j components. So these vectors always point in the j direction. So that rules out this guy, this guy, this guy. It rules out A, B, and E. Yes? Because none of those guys have j components. So now we're just left with figuring out what does yj look like. Well, yj, when y is positive, it's pointing in the positive y direction, and when y is negative, it's pointing in the negative y direction. Which of the 3 remaining do that? Just D. Right, so when y is positive, you're above the xy axis, you have, it's pointing in the positive j direction, and when you're below, it's pointing in the negative j direction. We can keep going here. Number 2 has only j components. And so we're talking about either C now or F. Number 2, when x is positive, this thing points in the negative j direction. And when x is negative, it points in the positive j direction. So C. Should I keep going, or are we good? One more. Let's do, I don't know, this guy, 4. So that one has only I components. So that's got to be A, B, or E. When y is positive, this thing points in the negative I direction. So y is positive when it's above the x-axis. And when y is negative, this thing points in the positive I direction. What do you think? B? Yeah. Okay. Next.
Do you have any tips for if like we're given an integral or given a shape and we have to find something like, I don't know, tips for recognizing which theorem to use? Because I just get bogged down, you know, and kind of end up using this as a crutch or looking, you know, knowing that it's in the section.
I can sort of make up some stuff here. If you have a contour, let's start from the beginning. If you have a line integral and it's not a closed path, then you should think about using the fundamental theorem of line integrals. If you have a line integral and it is a closed path, then you should think about using Green's theorem. I'm not saying that you should, but these are things to think about. And both of those examples were in the plane. Okay, so if you have a line integral in the plane, actually not necessarily that one. So the first one, if you have an open curve at all, you should think about using the fundamental theorem of line integrals. The second one, if you have a closed curve in the plane, you should think about Green's theorem. If you have a closed curve but it's in 3 dimensions, right? Like maybe there's some surface or something, or it's a closed curve, but it's tilted somehow. Now you're talking about Stokes' theorem. If you have a surface and it's not a closed surface, you should be thinking about Stokes' theorem. If you have a surface and it's a closed surface, you should be thinking about the divergence theorem. And then in this particular chapter, if you have a volume, a bounded volume, you should also be thinking about the divergence theorem. Because it's the boundary is a closed surface, yes.
And then, like, if it asks for flux, then you do a flux integral. If it asks for divergence or curl, then you just do divergence or curl.
Sure.
Can you do number 3, please?
On
Webwork.
WebWork, no problem. Oh, more graphs, okay.
I'm not very good at this.
So determine whether the line integral of each vector field in blue along oriented path in red is positive, negative, or 0. So you'll remember that a stretch of line integral that's going against the force is negative. If it's going with the force, it's positive. And if it's perpendicular to the force, it's 0. Those are the three fundamental ideas. So we can look at this guy and we see that as we go along here, it appears we're going perpendicular, so there's no contribution here. We get a massive positive contribution here, no contribution here, and then we get a smaller negative contribution here. What do you think? Yeah. This guy, it appears that we move perpendicular here and perpendicular here, so I'm betting that's 0. This guy we move negative, 0, positive, 0, and my guess is these two guys balance out. So that's generally how you approach it. So that last one, that third one's probably 0. I'll leave the other 3 for you guys.
Well, number 6 or whatever. Is another picture one.
Determine whether the divergence of each vector field at the indicated point P in blue is positive, negative, or 0. Okay.
Is this similar to number 1?
Not really.
Okay.
So, you remember that divergence, I think the best way to think about divergence is whether there's compression or expansion going on at a particular point. And if there's compression, then the divergence is negative. If there's expansion, the divergence is positive, and if there's neither, then the divergence is 0.
Compression is when there's more going into it.
More going in than coming out. Yes.
And that's negative.
That's negative, yes.
And what's the opposite?
Expansion. More flowing out of that point than flowing into it. And I think the easy thing to remember is divergence, right? When I think of divergence, I think of things flying apart. Right? So that's positive. That's right. Otherwise, we wouldn't call it divergence. We would call it the convergence of F. Right? Okay. So it's negative. Negative divergence is convergence. Yeah. So this guy here, you can see that along horizontal lines, these force vectors appear to be constant. And there's also no sort of flow away in this direction, or everything's horizontal. So the divergence at this point P is going to be 0. Right? There's an arrow coming in that's exactly the same size as the arrow coming out. And there's nothing peeling off to the sides or coming in from the sides. This guy here, yeah, this guy here,
So it's getting small, the one going in is bigger than the one going out.
right. And there's also, there appears to be kind of stuff pinching in as well, maybe-ish. I don't know. But yeah, there's more coming in than going out, and so there's convergence there, so negative divergence. And how about this guy?
Divergence, because it's smaller going in and bigger coming out.
Yeah, and there's nothing really playing with the sides at all. Again, these are just all purely vertical. There's no eye components to these guys. So yes, there's a little guy coming in and a bigger guy coming out. Diverging, so positive.
What does it mean if it's pinching in? You're saying that like the middle one's pinching, maybe pinching in, but like we already know that it's converging.
Yeah, so I don't think it's really relevant to this particular example. I wish I could think of an example where it would be relevant, but you can imagine if all of these, it's hard, I'm not sure I'm going to help you here, but if you could imagine the same vector field where all the arrows were the same length, but pointing inward, it would still be negative divergence. And that's because there's kind of, along this line here, there's also this kind of tendency to pinch.
I see.
But I'm not going to ask you anything that subtle, okay? I'll just keep it simple, because the goal here is not to be able to stare at vector fields that are really complex and figure it out. We just want very straightforward examples. Nobody has like really great intuition about this kind of stuff. If you're really confused, take the divergence of the function and see what happens, okay? You're not given the function here, but...
Would be on the test possibly? There's a picture?
No, the pictures on the test will be very straightforward as well.
Like these ones?
Very much like this, yes. I wasn't even happy really with the pictures that I put on the review sheet.
You're more happy with these ones?
I'm more happy with this than with the ones that I put on that review sheet on the back page there. The first part of that problem I was happy with, but the second part that I asked about conservativeness, I wasn't happy with. I will make, if I ask you a question like that, I will make it much clearer.
Do you guys have any questions?
Is that just a simple, like, when you were saying, like, when it's closed, you mean, like...
Yeah, that, like, whether it's path independent or closed. God, I thought maybe it was Chelsea who was asking me that yesterday or today, earlier today. There was one where you had a path that went just from this point to this point, and then another path that went from here down to here, and then back up to this point. Do you remember that one?
Oh, that was on the web work.
Yeah,
That
that
was
wouldn't
on-
work.
That one wasn't working for me for some reason. I kept getting like I got the same work kind of done, like it was like -24 and then -24 again for some
Oh,
reason.
one of them
And it
should
should have
be
been
zero.
one of them. Well, no, it should be like -24 and +24. Like they should cancel out because
Because it was close.
Because
Let me try- let me-
But because it's
Let me try this one.
It was
Nope.
it was conservative. Oh yeah.
It was in the conservative?
It was in there. Oh, yeah. It's in the 16 review.
Oh, it is? Okay.
Yeah, it's like, yeah, it's.
This one?
Yeah, number 4.
Okay.
Yeah.
Did you also do one of the problems once you were saying that?
Yeah, this one. Okay. Yes.
I think I got number 1 to work.
So,
I couldn't
okay.
get number 2 to work.
So if you look at this thing, right, that F, it's conservative.
Yeah.
Okay. Which means it's independent of path.
Right.
So what you have to do is you have to do some work. You have to actually calculate this integral. But once you calculate this integral,
Right.
then these two are free.
Right. Well, I mean that one's just closed. So
2 is the same as 1,
Yeah. It's just this.
and 3 is 0.
Yeah.
because it's a closed path.
I mean, I did number 2 the long way, trying to verify, that
Okay, and it wasn't working out?
It wasn't working, so I think it was probably just an algebraic thing, but I'll remember.
You have to parameterize, you have to do 2 integrals.
Yeah,
Okay.
yes.
Yeah,
But-
but it should work out, and I think it came out to 0 the first one. Is that what you got?
I don't remember what I got, but,
Aren't they the same as they started with?
well, just number 3.
Just number
starts
3 is
with-
close.
Oh, well, 1 and 2 would be the same.
1 and 2 would be the same.
I think they're all conservative, so you could do.
Yeah, they're all 0.
They are all 0, but 1 is 0 just by accident.
Yeah.
1 is 0 just by accident. Yeah, I guess it is by accident. I was going to say it looked like it was perpendicular everywhere, but it's not perpendicular.
It kind of makes sense though, because if you look at it, each quadrant has like a line of symmetry in terms of the vector field, like a diagonal line of symmetry. So in terms of like how negative it would be near the y-axis in the second quadrant is probably about the same as how positive it's going to be near the x-axis in that quadrant.
Yeah, and you can definitely use that to inform, but ultimately you do have to compute this one.
Could you do like A
Sure.
or set it up?
So this appears to be a quarter circle, sorry, a half circle. Yes, they do tell you that it's a half circle. In my case, the circle is of radius 4, 1, 2, 3, 4. So I would parameterize that guy using 4 cosine t, 4 sine t. And it's just 2-dimensional, so. And you get your hands on R prime. And F here was, oh, sorry, I don't need to do that. I need to find little f. That's what you want me to do, right? Yes. I forgot this was conservative. 5x plus 2y, 2x plus 4y.
Wait, so what is, it's asking for the integral of f dot dr, it's asking for what?
Yeah, because this is conservative, so you can use the fundamental theorem of line integrals. So let me do it. 5x plus 2y.
And it's conservative when the gradient cross F is equal to 0.
It's conservative in this case when py equals qx. And, gosh, where was I? 2x plus 4y. How'd you make out, Heather?
Probably 1 by 71.
Oh my god.
Yeah, I know I play ball with you. Like, seriously, like,
You
how
won,
was it
wait,
like?
you won by 71?
Yeah, it was like 90 or so.
You guys have had some, like, and plus you went up and played Colorado College, and that was like a total waste of time, right?
Yeah, it's like.
When you could have been here
Yeah,
with
I know.
us.
So frustrating,
Okay, so,
Like, 5 or 7 is so bad.
They're just not
Like,
cheap.
high school is really better.
when did she switch to like the second 5? Halftime, or even earlier?
Even, yeah, like,
Okay.
first day.
Got it. See, nobody remember that kid that scored 138 points a couple
Yeah.
weeks ago.
Yeah.
Nobody talked about how uncool that was. That's
Yeah,
not cool to
seriously.
be beaten up on like whatever Iowa Bible College or
Yeah,
something. That's
it's
just not
sad.
cool, right? He's
Well,
there's
but
2
they
minutes to
both
go, and
did
this dude is
score. Yeah.
draining threes,
Yeah.
right?
Well, they both scored. There was no defense in that game.
Yeah, I mean, it's
And-
true.
And because the thing is that the other team, like the team that kid was on, they still had people like scoring.
Yeah,
Still people.
it was silliness all the way around. Okay, back to this. So when you have this thing, when you identify this thing as conservative, so you do this test, piece of y is 2, q sub x is 2, yay, it's conservative, then you immediately say, oh, well, this must be f sub x and this must be f sub y, and you go through that process of finding f. You know, I've seen some variations on this process that may be a little unsafe. This is the process that you should follow. So you start out with f sub x is 5x plus 2y. And you anti-differentiate to get f. So that's going to be 5 halves x squared plus 2yx plus some constant that might depend on y. Right? Okay, now differentiate this with respect to y. That goes away, the other guy turns into 2x, and this turns into c prime of y. And you know that that has to equal 2x plus 4y from this guy up here. Often you'll get some cancellation like that, and you'll know that you've made a mistake if what's left has an x in it. C of y is then 2y squared like that, plus some constant, say d. Now we've figured out what c of y is, and we know what all of f is. It's 5 halves x squared plus 2yx plus 2y squared plus some constant d. Once you know f, then you're ready to use the fundamental theorem of line integrals. And in this case, the curve started at 4, 0, and it ended at negative 4, 0. So what you would do to compute this line integral is you would do f of negative 4 comma 0 minus f of 4, 0. The end point minus the starting point.
Is this counter?
This was counter, well, yeah, the orientation matters. And this guy starts out at 4, 0 and ends up at negative 4, 0. Yes.
So this is an application of the fundamental?
Yes, it is. Yes. Mm-hmm.
I wonder if you can do
Yeah.
16.6, number 12.
16.6, number 12. Okay, so the area of the cone that lies above the interior of the circle given in polar coordinates. So, I would parameterize this using polar coordinates, because the region of integration, all of this is happening above something that looks very polar. Okay, so what is this? Z equals k root x squared plus y squared. This is problem 12, 16, 6, 12. Like that. Now, to parameterize this in polar, I keep using, well, I'll use u and v. This is going to look like u cosine v, u sine v, and then that thing there turns into just ku. All right? Ru is cosine v, sine v, and k. Rv is minus u sine v, u cosine v, and 0. Ru cross Rv is negative k u cosine v negative k u sine v and u. The magnitude of that thing is going to be, well, there's going to be a u that comes out. Well, let me just do the whole thing. K squared u squared cosine squared v plus k squared u squared sine squared v plus 1 to the 1/2. The cosine squared term and the sine squared term combine to give me, oh, sorry, that's a u squared out there. My bad. The cosine squared, sine squared terms combine to give me k squared u squared plus another u squared, I guess. And that's going to simplify to k squared plus 1 square root times u. So
So that's a u squared?
Mhm.
There it was a 1?
Yes, that was my mistake. All right. So this,
Actually not u squared up front.
right here you mean?
Yeah.
Okay, so I've got a u squared here and a u squared here and a square root, and it just factors out right
Oh, you
there.
took the square root of that?
Yeah, exactly.
Okay.
Okay. Now, remember that the surface integral looks like this. And we've just computed this part. It remains to do limits of integration. Now, playing the role of r in our polar coordinate system is u, and playing the role of theta is v.
And just to clarify, when you've already converted to polar before you're doing integral, you don't have to.
Exactly. Now we're talking about above this area in the xy plane, a cosine r equals a cosine theta. This is a circle.
Are we given that information?
No, this is something that you would have to know. So this is a circle of radius a, sorry, of diameter a. And it is traced out as theta goes from minus pi over 2 to pi over 2. And it's traced out in this direction. Doesn't really matter, but that's how it's traced out. How do we make u and v describe that? Well, u is radial segments, so u starts here and goes out to the curve everywhere. So u is going to go from 0 up to a cosine theta, and theta is going to go, sorry, cosine u. V, sorry, v. And v is going to go from minus pi over 2 to pi over 2. And then you just do the integral. And
We just have to know that?
yeah, know what? Yes. Well, no, I mean, so these limits of integration describe this region. And if you don't remember that, that goes way back to...
So r is the diameter there?
No, a is the diameter.
A is diameter.
Yes.
Just to clarify my earlier question,
Mm-hmm.
it's, you don't tack on the R when you measure parameterization.
In terms of those guys,
But if
right?
you did your
Cartesian.
Cartesian, and then like after you calculated RU cross RB and you converted to polar, then you still have, okay.
Yes. When you do a change of variables, then you have to do the polar Jacobian or the spherical Jacobian.
This may be a very primary question, but when would you know whether to convert to polar or
I tend to do it when I see like x squareds plus y squareds, things like that. So, for example, what kind of pushed me in that direction, there were two things in this problem that pushed me in that direction. One was the fact that this was x squared plus y squared right here. And the other was the description of the domain of integration here. And both of those things strongly suggest to me that I should do polar from the get-go, or at least polar at the end. Heather.
I have a question on 16.5, number 1. I wasn't sure how to deal with or like parameterize an R of U and V, where I could then know N or compute N.
Okay, so in neither of these cases, let me just make sure I'm about to speak the truth. We're in the Green's theorem section, so what you want to do is use these formulas up here. Let me find them for you. So here's the f dot dr formula. And so you jump over to this guy. And then there's the f dot n somewhere, maybe down below, I don't know.
Yeah, it's
And there's the f dot n guy down here. So that guy goes to this guy. Okay, so that's what you're applying in this particular section, is those two identities. Whenever you encounter those guys, that's where you're headed. So let's look at problem 1 here, and let's look at the domain. The domain here is just a square, 0 to 1, 0 to 1 in the xy plane. And you take f dot dr and you convert it to this guy up here, 16.2. So this is really just about computing the curl of f. So let's look at f. F is xy minus xy. To take the curl of that thing, you don't really need to do the curl. You can just kind of memorize. But to take the curl of that thing, tack on an extra coordinate, a z coordinate that's 0. And don't compute the whole curl, just compute the k component of the curl. Because ultimately you're going to dot it with k. K is 0, 0, 1, exactly. And really, that's just extra work. If you just want to remember that f dot dr is this thing. Sorry, f dot dr is this thing here. If you just want to remember that, that's probably the easier thing to do. That's just Green's theorem.
Right.
So I think if I encountered an f dot dr in that context, I would just go Green's theorem.
So I just take F cross del and then.
You could do that. Okay, so I'll just do it. Okay, so that's no problem. Come on. Read me F, Heather.
Let F equal the vector function xy followed by negative xy, and let D be given by 0 less than or equal to x less than or equal to 1, and then for y it's 0 less than or equal to y.
Yep, okay, and then I want to do...
Compute the integral of dr and the integral of f.
Okay. So this guy we know is the integral. Oh God, what is it? Is it qx minus py? Thank you. dA, and then this guy is forget.
Or just FXF?
I don't know why I'm drawing a blank here. Sorry, what is it?
Is it just FXF on
dx plus qy?
A negative q dx plus p dy.
Negative q dx, right. Negative q dx. No, that's not what I'm doing. Yeah.
Just px plus qy.
It's
dA.
Yeah.
I'll just look it up. I don't know why I'm drawing a blank. Oh, divergence theorem, duh, yes. Okay, that's why I'm drawing a blank. Okay, so you've got these guys. Let's do this thing. So this is P, this is Q. All right. So let's do one first. So Qx is negative y. Py is x. Yeah? Okay, so then we get the double integral. It's just 0 to 1, 0 to 1. Qx is negative y, and py is x, and then it's just dy dx or dx dy, however you want to do it. Okay, and then for 2, so then I'll leave that integral to you. And then the gradient, the divergence of f is this guy. Yep. Okay, so the divergence of f is that guy. That turns into y and minus x, and then integrate that thing over the area. Now, and especially when you're dealing with constant limits of integration like this. So, yeah, just sort of memorize those formulas and you'll be okay. Or even better, sort of see how they flow from Green's theorem. I've been recording this, so if you want to check, especially you, Heather, when you came, since you came in late. So I'll post this on the YouTube channel, and I don't know, maybe there'll be some stuff there that'll be useful to you. It's pretty disjointed, but yeah. I'm going to bed. I will be around in my office most of the morning, prepping for differential geometry and proofreading the exam that I wrote this afternoon for you guys. So you can knock if you have a quick question, but I'm not going to be able to spend a whole lot of time with you guys tomorrow morning.
Do you have our homework?
I do, yes. I'll run and get that. Let me shut this down. And yeah, or you can just